A practical electromagnetic system involves several uncertainties like material properties, surface defects, structural uncertainty, and orientation of radiating systems. For example, consider this figure. This is a cross-section of an aircraft radar. There is a radar antenna inside the structure. It is crucial to have proper beam pointing and scanning capabilities for this antenna to detect the ground presence. There can be several uncertainties in this antenna radiation setup, which can hamper the performance of the radar. At the time of mounting, there can be uncertainties in the position and orientation of this antenna. The radar wall affects the antenna gain and radiation pattern. This wall consists of multiple layers of material, which can induce uncertainty in the effective material parameters. The shape of the radar may be uncertain. Moreover, when it is airborne, there can be further uncertainties that can be accounted to vibration, temperature, and pressure. In a simulation environment, generally these uncertainties are unaccounted. Commercial EM software tools uses deterministic parameters. They usually ignore these probabilistic deviations. Sometimes, Monte Carlo simulations or adaptive Monte Carlo simulations are used for these uncertainties. But such methods are time consuming because of the repetitive simulations involved. We propose a computationally efficient and generally applicable method to predict the stochastic variation which can be used in a practical electromagnetic simulation. Stochastic analysis is broadly classified into non-intrusive and intrusive. In non-intrusive, the deterministic solver is considered as a black box. The results from multiple runs from the deterministic solver is analyzed to get the stochastic response of the system. The examples are Monte Carlo and stochastic collocation. Intrusive method reformulates the deterministic mathematical formulations to incorporate the stochasticity in the system. Spectral stochastic methods, perturbation method, and Neumann approaches are some of the examples. We use intrusive methods since it allows seamless tweaking of deterministic, stochastic, and numerical parameters, even though the implementation is complex. But this needs an in-house developed deterministic implementation. Out of the three intrusive methods mentioned, the spectral stochastic FEM or SSFEM can have the largest input parameter deviation as long as they are physically feasible. Moreover, the spectral stochastic FEM gives a sparse metric system with block structure which allows faster solution with limited computer space. First, we applied the SSFEM in material variation and developed a framework to analyze the effect of such dielectric variations in multiple subdomains of the model. The SSFEM system of equation is obtained by replacing the relative permittivity epsilon r in the deterministic FEM equation with a random variable. As a consequence, the electric field will be random. An unknown random field can be represented using polynomial case expansion. PCA represents a random process with a countable number of random variables. The effective stochastic metric system can be obtained by employing a Galerkin's testing on this equation. This produces a large metric system, but the metric is sparse. The unknown PCA coefficients are evaluated by solving this matrix. It can be seen that the SSFEM is very fast compared to the Monte Carlo. The SSFEM method discussed in the previous slide is extended for spatial variation in 3D. The correlation of spatial variation is represented using a covariance function. This covariance function is utilized to mathematically model the spatial variation with minimal number of random variables using Carhonen-Loewe expansion. The KL expansion gives accurate results when compared with MC simulation estimations using case test. The number of random variables per stochastic region is at least 4 when spatial variation is involved. This would increase the stochastic dimension beyond computational capability. To tackle this issue, we propose a spatially averaged SSFEM which would reduce the KL expansion to an equivalent dielectric constant varying as a single random variable, the mean and standard deviation of which is evaluated by spatially averaging the KL expansion. This would reduce the stochastic dimension to one random variable per stochastic region. This allows faster computation of EM response response when multiple spatially varying regions are present in the model. A comparison of SA-SSFEM, SSFEM and SC is given in the table. Stochastic geometric variation is rarely handled in electromagnetics. The intrusive forms are generally achieved by a scaling factor or by converting the geometric variations to material variation. This would limit the applicability of the method. The challenging aspect in geometric variation is the handling of associated mesh modifications. Apparently, mapping stochastic geometric changes to stochastic mesh updates remained a challenge. We propose a method to handle geometric uncertainty as it is by employing pure transformation. This is the first work towards the full wave intrusive formulation of geometric variations. The changes in geometry is mapped to the individual tetrahedrons. The basis functions associated with these tetrahedrons are mapped to a reference tetrahedron for evaluating FEM matrices. This mapping involves pure transformation due to the vector nature of the basis function. The stochastic changes in shape of tetrahedrons are brought into the Poisson transformation to formulate geometric SSFE. The results are compared with Monte Carlo using case test to verify the accuracy of the method. In the table, you can see that there is a comparison between GSSFEM, Pascal SC, both in console and in-house.